Here we're looking at a problem related to conservation of energy. And as is often the case, as we get deeper into the physics here, you're going to see problems have more than one concept represented. I chose this one from the 2004 AP Physics exam. Yes, it is related to conservation of energy, but we also have a stated circular arc with a known radius, and so we might have to get into uniform circular motion as we analyze this position A at the top of that circular loop. We are given some numerical information, both in the problem statement, you see a lot in the picture as well, and our goals here are to find the speed of the cart at point A, and also the magnitude of the force on the cart by the track, also at point A. Something to consider conceptually before we begin would be this statement of negligible friction. In science classes, negligible is just a fancy word for too small to matter, so there is too little friction in this question to consider it. And so we're going to avoid not only friction, but any work from friction, and that's what makes this a conservation of energy problem. Friction is one of the major external forces. I also can't think of any other external forces doing work, so we're going to have a conservation of mechanical energy in this problem. First step of that is to consider what energies we have at our two key moments. Key moment number one is where we have a lot of numerical information at the top of this first hill, and key moment number two will be the point in question, point A, at the top of the second hill. As we consider which energies are present at our two key moments, we would want to set a reference point. This is where the height is equal to 0. It is up to us as the problem solvers to set this point, and now we can measure heights since we have a reference. So looking at our first hill, we certainly have a height above that hill, 2 meters is given. So there is a gravitational potential energy stored in the cart. It has the potential to fall downward, and this bar will represent how much gravitational energy we're dealing with. This is also a moving cart. It has an initial velocity of 1.5 meters per second. Kinetic energy is related to motion, so we have a certain amount of kinetic energy here in this first graph as well. It doesn't really matter how tall you make these bars initially, but as we look at the similar energies at hill 2, we'll want to think about how tall to make those bars in reference to the ones we've already drawn. So looking over at the second hill, it also has a height above our reference point, now 1.9 meters. So we do have a gravitational potential energy again, but not as much as we had in the first graph, being that we are now closer to the reference point, 1.9 meters versus 2 meters. Kinetic energy, we would have another value here as well. We are expecting to be moving. We are solving for the speed there, so we want to have something to solve for. And this is conservation of energy. Since gravitational energy has decreased from moment 1 to moment 2, something else has to increase to conserve the total energy, and my only option for that is kinetic. So I'm expecting the cart to be moving faster at position A. We started with 1.5 meters per second. When I get to A, because I'm lower on the track, I should be moving faster, so I'll expect my final answer to be greater than 1.5 meters per second. This is a conservation of energy equation. I am writing this based on the graphs. The total energy of graph 1 should equal the total energy of graph 2. Since we see gravitational potential energy and kinetic energy in our equation, we'll go to the formula sheet to look up our kinetic and gravitational potential formulas. This is me just subbing those in. I see the variable m for mass in all 4 terms, so that's something I can divide out. I don't need to plug in the mass to solve question A. This is just establishing the given information. The goal is to solve for variable v2, and now we know everything other than that variable. Final answer is here, 2.05 meters per second, and since that is greater than 1.5 meters per second, that's a good sign. Next, let's attack question B. We're looking for a force. And notice nothing in the variables I've established through energy are force related, so I'll have to get another concept involved here. Centripetal force is a concept to review, specifically the variable Fc. This is the net force for circular motion, and it is always directed towards the center of the circle. That's how something is able to turn. So we draw a force diagram for the cart when it's at position A. 2 forces exist, a downward gravitational force from Earth and an upward force from the track, a normal force. We're being asked to find the force from the track, and this is the one now we should be hunting for, Fn, since it is provided by the track. Because the net force needs to point inward, that makes gravitational force larger than normal force. Notice how gravitational force would point towards the center of the curve, and normal force points away. That's why gravitational force is larger. My centripetal force equation is in minus out, large minus small. Here, Fg minus Fn. And all I'm doing here is copying that equation in a place where I can work around with it. Some substitutions we're going to need. We see gravitational force in our equation, so the weight equation will be useful. And whenever we see centripetal force, remember that's a net force, but with a specific centripetal acceleration. So we'll want to plug this in for A. So line 2, I'm just making those substitutions. Another one for the AC variable. And now establishing the given information, M, V, R, and G. And that leaves normal force as the only unknown variable. So performing the calculation gives me a normal force of 2.69 newtons. And that will be the answer for question B. So I can't say this is the hardest question you'll see in AP Physics, but it's a good one to review strategies for each major concept, energy and circular motion, and also just as an example of a question that deals with two major topics at once. If you found this video helpful, then I have other resources that you may be interested in as well. For more information, check out my website, shoot me an email, or follow me on X and Facebook. All of the links can be found in the video description.